On with the field effect transistor amplifiers and switching circuits, chapter 9, section 9.1, the common source amplifier. Right, before we carry on, let's have a look at the introduction in our textbooks. On page 236, the introduction there, it says, because of their extremely high input resistance and low noise, some of the characteristics that we've learned in the previous chapter, field effect transistor amplifiers are a good choice for certain applications such as amplifying low-level signals in the first stage of a communication receiver. FETs are also have the advantage in certain power amplifiers and in switching circuits because biasing is simple and more efficient. The standard amplifier configurations are common source, common drain and common base, which are analogous to the common emitter, common collector and common base configurations of the BJTs, also because of the three terminals. Field effect transistors can be used in any of the amplifier types introduced earlier, Class A, Class B and Class C. In some cases, the field effect transistor circuit will perform better. In other cases, the BJT circuit is superior because BJTs have higher gain and better linearity. Another type of amplifier, Class D, is introduced in this chapter because field effect transistors are always superior to BJTs in Class D, and you will rarely see BJTs used in Class D. The Class D amplifier is a switching amplifier that is normally either in cutoff or saturation. It is used in analog power amplifiers with a circuit called a pulse width modulator, which is introduced in section 9.4. Field effect transistors are superior to BJTs in nearly all switching applications. Various switching circuits, analog switches, analog multiplexers and switched capacitors are discussed. In addition, common digital switching circuits are introduced using the CMOS, a complementary carbon oxide. Alright, the first one we're going to look at is the common source amplifier. I didn't underline it this time, but the introductory paragraph, you can mark that. When used in amplifier applications, the field effect transistor has an important advantage compared to the BJTs due to the field effect transistor's extremely high input impedance. Disadvantages, however, include higher distortion and lower gain. The particular application will usually determine which type of transistor is best suited. The common source amplifier is comparable to the common emitter BJT amplifier that we studied in chapter 6. But we will see the similarities as we go through the circuit. Alright, on that same page 437, we can see there's an equivalent field effect transistor model. In part A, the internal resistance, RGS, appears between the gate and the source, as we can see in figure 9.1a. Alright, and a current source equal to GM VGS appears between the drain and the source, as also indicated in there. Also, the internal drain to source resistance, RDS, is included. In part B, a simplified ideal model is shown. The resistance R accent GS is assumed to be extremely large so that an open circuit between the gate and source can be assumed, as we can see there. And also R accent DS is assumed to be large enough to neglect. Alright, so an ideal field effect transistor circuit model with an external AC drain resistance is shown in figure 9.2. The AC voltage gain of this circuit is V out over V in. Always the gain is V out over V in for all amplifiers. But in this case, where V in is equal to VGS and V out is equal to VDS. So the voltage gain expression then is voltage gain is VDS over VGS, V out over V in. And then from the equivalent circuit, VDS is IDRD, and from the definition of transconductance, VGS is ID over GM. And that then all simplifies, if I substitute and simplify, equation 9.1 on the next page. where I can see if I substitute and simplify, I get that the voltage gain is GM times RD. If we go and have a look at example 9.1, where they just use this formula, a certain JFET has a GM of 4 millisiemens. Remember, it's the reciprocal of resistance. With an external AC drain resistance of 1,5 kilo ohm. What is the ideal voltage gain? Just use the formula, put the values in, and in this case it works out to be 6 voltage gain. And remember, some of you still included a unit when you talk about voltage gain and current gain or whatever. Remember, there's no unit, just a ratio. No? So you can't say voltage gain is equal to 6 volts, for instance. Right? No unit. You will lose your marks if you use units. Anyway, let's have a look at the common source JFET amplifier. We can just have a look at figure 9.3. There we can see we have our amplifier. Common source. How did we distinguish between the different amplifiers? Can you still recall for the BJT? I had to look, where's the input? Where's the out? Which terminal is the output? The remaining terminal, which are common. If you will have a look here, input signal here is at the gate. There's my input signal. Output signal, there's my load resistors at the drain. And I can see here for AC and DC, because the AC will pass the capacitor acts as a short for AC signal, are both common to ground. So it makes it a common source amplifier. Alright. Also, if I go and look at the input and output signals, you can see here, as they are shown here, input signal, output signal, I can see it's amplified on the output, and also the same as for the common emitter amplifier, it's 180 degrees out of phase as well. Alright. Alright, so let's refer back to the textbook so that you can mark what I've marked there. Common source JFET amplifiers, the one with the AC input signal is applied to the gate, and the AC output signal is taken from the drain, as we've seen. The source terminal is common to both the input and output signal. A common source amplifier either has no source resistor or has a bypassed source resistor so that the source is connected to AC ground. A self-biased common source N-channel JFET amplifier with an AC source capacitively coupled to the gate is shown in figure 9.3a. Alright, that's another thing that we should have seen, which I didn't point out, is the type of biasing that's been used. Alright, so I can see it's not voltage divider biasing in this case, but it is self-biasing. I have to determine the value of RS to determine my Q point. Alright, the resistor RG serves two purposes, as I've underlined here. It keeps the gate at approximately 0 volts because IGSS is extremely small, and its large value, usually several mega ohms. Remember, in previous examples we used 10 mega ohms, and it prevents loading of the AC signal source. A bias voltage is produced by the drop across RS, as we just see, as I just told you, cell biasing, and then the bypass capacitor C2 keeps the source of the JFET at AC grounds. I can see here, bypass capacitor used. Anyway, the input signal voltage causes the gate to source voltage to swing above and below its Q point value, VGSQ, causing a corresponding swing in the drain current. Let's just have a look at that figure. Similar to the figures that we've seen for the BJT, only in this case they're using the transfer characteristic curve to show the signal operation, and also the drain curves with a load line. Right? Of course, this one looks very similar to the BJT we've discussed for the different IBs. Remember, as I changed IB for the BJT, then of course IC changes. In this case, of course, it's VG that keeps on changing to change ID. It's a voltage control device. Alright, but I can see on here from the Q point all that they were saying there. as I increase and decrease around the value of the Q point, I can also see that ID increases and decreases, but because it's 180 degrees out of phase, first, if ID increases, and then of course I can see it's moving towards the 0 point, I can see then that VGS is decreasing 180 degrees out of phase. And I can also see it here on the transfer characteristic curve, swinging there around the Q point. Here I can see first if VGS increases, I can see that ID decreases and vice versa. Alright, on the transfer characteristic curve. But it's discussed there in the textbooks as well. On page 438, the drain to source voltage swings above and below the Q point value and is 180 degrees out of phase with the gate to source voltage, as I've underlined there. Right, the graphical picture, as I've just explained on figure 9.4, you can see also there as VGS swings from its Q point value to a more negative value, ID decreases from its Q point value, and as VGS swings to a less positive or a less negative value, ID increases, of course. Alright. And you can perhaps just underline, that's interesting as well, on page 439, the last sentence there. Because the transfer characteristic curve is non-linear, the output will have some distortion. Remember? It's a non-linear curve, no? So what they say, this can be minimized if the signal swings over a limited portion of the load line. So as long as I don't use a large portion of the load line, the distortion will be less, because if I use a smaller portion, that's the section that I'm using looks more like a straight line, so then the distortion will be less. Alright, the DC analysis, the same as we have done with the BJT. Common source amplifier, figure 9.5. What is the important thing? To simplify the circuit, it's all about the capacitors, no? Right, we're looking at DC first. So what happens to the DC? It blocks the DC, so I can just remove those portions of the circuit and it simplifies down to this. Right, so you can see the capacitors are removed because it blocks the DC. So I will be just working with that portion of my circuit, which of course would have been important if there was a load resistor and an input, because then they will be removed, of course, now, as we've seen with the BJT. Alright, the first step in analyzing a field effect transistor amplifier, if we look in the textbook, let's just make it a bit bigger. The first step in analyzing a field effect transistor amplifier is to determine the DC conditions, including ID and VS. ID determines the Q point for an amplifier and enables you to calculate VD, of course, so it is useful to determine its value. And as we know, it can be found either graphically or mathematically, as we've seen in the previous chapter. The graphical approach introduced in chapter 8 using the transconductance curve will be applied in the amplifier here. The same result can be obtained by expanding equation 8.1. Remember, which says ID is equal to IDSS in brackets, then 1 minus VGS over VGS off squared. Alright, as we've seen, the capacitors then are removed. Graphical approach, I'm not going to do it again. Remember, it was in the previous chapter, as you can see on top of page 440 there. Recall from section 8.2 that the JFET universal transfer characteristic curve illustrates the relationship between the output current and the input voltage. The endpoints of the transconductance curves are at IDSS and VGS off, and a DC graphical solution is done by plotting the load line for the self bias case as shown. Remember, as we've done as well. Remember, you know how to do this. And remember, cell biasing, I know how to. I have to determine when ID is equal to 0, then of course VGS is also equal to 0, and the other one was where ID is equal to IDSS. Then I had to determine that value so I can plot the second point, connect the two lines and get the load line. Remember to make sure that you know if you're working with a cell bias or a voltage divider biased circuit. Anyway, let's have a look at example 9.2 in the textbooks. Want to point out something there as well. That's important. The question is, determine ID and VGS at the Q point for the JFET amplifier in figure 9.6. The typical IDSS for this particular JFET is 4.3 milliamps and VGS off is minus 7.7 volts. Now the solution, you have to plot the transconductance curve because it's not given. But you know how to do that. In this case I want you to underline, because this was a shortcut that was used that you also can use for this type of problem. It says there the endpoints that are at IDSS and VGS off, as you know. If I look at the curve here, I know that I can already plot those 2 points. Either be given or I get it from the data sheet. But what is important, you can plot 2 additional points quickly by noting from the universal curve in figure 8.12 that VGS is equal to 0.3 VGS off, and VGS is also 0.5 VGS off. So I can plot another 2 points on that curve. Where does that come from? If you will leave back to the previous chapter where we have discussed the transfer characteristic curve, it was mentioned there on page 376. Remember where we discussed the JFET universal transfer characteristic curve? There it was mentioned. Remember we said ID is equal to 0 when VGS is equal to VGS off, and ID is equal to IDSS when VGS is equal to 0. But also it said here IDS is divided by 4 where VGS is equal to 0.5 VGS off. ID is equal to IDSS divided by 2 when VGS is equal to 0.3 times VGS. Alright, so just to remind you where that comes from, so you can quickly plot, so you don't have to, in this specific case, go and plot the whole thing where you have to calculate ID at 1 volt steps. Remember we did it previously in 1 volt steps. Minus 1, minus 2, minus 3 until the VGS off. So this is a quick method to draw the curve so that you can do your calculations here. Now anyway, for this particular JFET, the points are plotted as shown in figure 9.7a. Recall from chapter 8 that the load line starts at the origin and goes to a point where ID is equal to IDSS and VGS is equal to IDSS-RS. Add the load line to the graph and read ID and VGS values from the intersection. The Q point is shown, and from this graph I can see that ID is equal to 2.2 milliamps and VGS is equal to minus 2.4 volts. Alright, so a quick method here. Just note here the mathematical approach at the bottom of the page. Remember we said there are 2 methods. The mathematical approach is more tedious. Alright, more tedious because it involves expanding the equation into a quadratic form and solving the quadratic equation, which is a long mathematical thing, and we haven't got time for that lots of mathematics, so we're not going to use that method. But you can do it though. They say here on the top of the next page, a much easier approach is to enter the equation into a graphing calculator. Alright, but I think most of us do not have graphing calculators, so we are not going to do the mathematical method. We will use the graph as in the previous example. Anyway, so you can use that formula if you do have a graphing calculator. ID is equal to IDSS in brackets 1 minus ID RS over VGS off squared, and then of course you can see the mathematical problem getting ID from that formula. But there, example 9.3 shows you how to use it on the graphing calculator. Anyway, that's the DC part. Let's have a look at the AC equivalent circuit. To analyze the signal operation of the amplifier in figure 9.5, develop an AC equivalent circuit. Can remember what I have to do. Goes about the capacitors and the DC supply again. Replace the capacitors by effective shorts based on the simplifying assumption that XC is equal to 0 or equivalent to 0 at the signal frequency, and replace the DC source by a ground. Remember, the same as what we've done with a BJT. Alright, so in the end, the circuit simplifies to that. Okay, remember, there's a load resistor, the same as we had with the BJT. Then I have to calculate R small d subscript, which is RD in parallel with RL. Ne? And of course, you can already imagine, as we will see just now, that it has an influence on the voltage gain. Anyway. Okay, the AC equivalent circuit is shown in figure 9.8a. Notice that the positive VDD end of RD and the source terminal are both effectively at AC ground. Recall that in an AC analysis, the AC ground and the actual circuit ground are treated as the same point, as we can see here on the circuit as well. Alright, now signal voltage at the gate. An AC voltage source is shown connected to the input in figure 9.8b. Since the input resistance to a FET is extremely high, practically all of the input voltage from the signal source appears at the gate with very little voltage drop across the internal source resistance. So VGS is equal to V in. So the voltage gain, the expression for voltage gain, as we've seen, voltage gain is equal to GMRD. The output signal voltage VDS at the drain is V out is equal to VDS is voltage gain times VGS. Remember, look at all the subscripts. Lowercase now, so it means we're working with AC. V out is equal to GM RD V in, where RD, underline that, of course R lowercase d is RD in parallel with RL, and V in is equal to VGS. But anyway, let's have a look at example 9.4. Example 9.4, what is the total output voltage for the unloaded amplifier? Unloaded amplifier in figure 9.9. IDSS 4,3 milliamps, VGS off is equal to minus 2,7 volts. Let's have a look at the solution. On the next page, use either a graphical approach as shown in example 9.2 or the mathematical approach with the graphing calculator, which is not an option for us. They used the mathematical approach with the graphing calculator here in the textbook. Of course, you'll have to go and do the graphical approach. Né? Please make a note. To determine ID. Alright, so say they took a quick method using a calculator to determine ID. But remember, in the previous example, they've shown you how to determine ID graphically. Né? Alright, so now they've got an answer of 1,91. Your answer may differ a little bit because it's determined graphically. And then using this value, I have to go and do the next calculations. VD is equal to VDD minus IDRD, 12 volts, the supply, minus the 1,91 milliamps that I've just determined graphically, times R value of RD 3,3 kilo ohms gives me a value of 5,7 volts. Just remember to work your answers accurately to 3 decimals. Next, I can calculate GM. VGS is equal to minus IDRS minus 0,9 volts in this case. GM 0. This formula is also from the previous chapter. If you recall, you did some examples and basic problems in the previous chapter determining and using these two formulas. 2 times IDSS and absolute divided by the absolute value of VGS off. 3,18 millisiemens. And GM, this formula again, GM0 in brackets 1 minus VGS over VGS off. 2,12 millisiemens, not seconds, millisiemens. Finally, you can find the output voltage, which is voltage gain times V in, which is GM times RD times Vn, and in this case, 700 millivolts. So I can see the input signal was 100 millivolts, and the output is 700 millivolts. So I can see here that the gain was 7. In this case, now 7 times 100 is going to give me 700 millivolts. Alright, then the effect of the AC load on the voltage gain. Remember, we did the same approach for the BJT. We had a look at what was the effect of changes in the circuit. When a load is connected to an amplifier's output through a coupling capacitor, as shown in figure 9.10a, I can see how did the circuit now change. Input signal there connected, but also a load resistor. So what do I have to do? I have to calculate RD in parallel with RL. That is going to be my load. Alright, so the effect of RL is to reduce the unloaded voltage gain. Let's go and have a look at the example in the textbook. On page 444, example 9.5, if a 4,7 load resistor is AC coupled to the output of the amplifier in example 9.4. So they're using the same circuit as previously, where we found an output voltage of 700 millivolts. What happens now if the load resistor is connected? R small d, which is RD in parallel with RL. So now the resistance now drops from 3,3 to 1,94. Ne? So calculation of V out then yields that GM times RD times V in is now going to give me only 411 millivolts. As previously I had 700 millivolts for that same circuit without the load resistor. So make a note of that. Right, the next section, the phase inversion. The output voltage at the drain is 180 degrees out of phase with the input voltage, as we've seen. Input resistance, because the input to a common source amplifier is at the gate, the input resistance is extremely high. Ideally, it approaches infinity and can be neglected. As you know, the high input resistance is produced by the reversed biased pin junction in a JFET and by the insulated gate structure in a MOSFET, as we've seen in the previous chapter. The actual input resistance seen by the signal source is the gate to ground resistor RG in parallel with the field effect transistor's input resistance FGS divided by IGSS. The reverse leakage current IGSS is typically given on the data sheet for a specific value of VGS, so that the input resistance of the device can be calculated using equation 9.4. So Rn is then Rg in parallel with VGS over IGSS. Since the term VGS divided by IGSS is typically much larger than Rg, the input resistance is very close to the value of Rg. Alright, so we can have a look at the example, so we can just assume then that the input resistance is equal to Rg. Alright, but if we look at the example 9.6, the input resistance is seen by the signal source in figure 9.8. What is the input resistance? IGSS is equal to 30 nanoamperes at VGS of 10 volts. So if I go and calculate the input resistance at the gate, the top of page 445, the input resistance at the gate of the JFET is 10 volts divided by 30 nanoamperes is 333 mega ohms. So the input resistance seen by the signal source is Rg in parallel with that R in at the gate. And what do I know about two resistors in parallel, and the one is much larger than the smaller one? The total resistance will be close to the value of the smaller one. So for all practical purposes, R in can be assumed equal to Rg. Please make a note of that. Alright, just the last two sections here for this specific section. D MOSFET amplifier operation. A zero biased common source N channel D MOSFET with an AC source capacitively coupled to the gate is shown in figure 912. The gate is approximately 0 volt DC and the source terminal is at ground, thus making VGS equal to 0 volts. So the signal voltage causes VGS to swing above and below its zero value, producing a swing in ID as shown in figure 913. Depletion enhancement operation for the D MOSFET shown on the transfer characteristic curve, as I can see here. Here's my Q point, remember. So it's operating in the enhancement and in the depletion region. And I can see here as I'm changing around the Q point, also VGS and ID is also changing there. So the negative swing in VGS produces the depletion mode, as I can see on that portion. Alright. And ID decreases. The positive swing in VGS produces an enhancement mode and ID increases. So I can see the two sections that it works in. Note that the enhancement mode is to the right of the vertical axis and the depletion mode is to the left. The DC analysis of this amplifier is somewhat easier than for a JFET because ID is equal to IDS is at VGS equal to 0 as we can see on that curve. No? Anyway, so the AC analysis is the same for the JFET amplifier. Alright, so the E MOSFET amplifier operation, a common source on page 446, a common source N-channel E MOSFET with a voltage divider bias with an AC source capacitively coupled to the gate is shown in figure 914. The gate is biased with a positive voltage such that VGS is much larger than VGS threshold. As with, can underline this as well, as with the JFET and the D MOSFET, the signal voltage produces a swing in VGS above and below its Q point value VGSQ. This in turn causes a swing in ID above and below its Q point value IDQ as illustrated in 915. And it's entirely in the enhancement mode, as I can see here. Remember, we've had a look at the characteristic curves of these two devices, E MOSFET and D MOSFET. So you just have to remember which one to use, but I can see now it is completely in the enhancement mode, that it swings around the Q point. Alright, at the bottom of page 446, example 9.7, transfer characteristic curve. Transfer characteristic curves for a particular N-channel JFET, D MOSFET and E MOSFET are shown in figure 916. Then they ask to determine the peak-to-peak variation in ID when VGS is varied plus minus 1 volt about its key point value for each curve. So in comparison then, you can see the three different curves there. For the JFET, the D MOSFET and the E MOSFET, you can see the different curves being used. Then I can go and calculate. The JFET Q point is at VGS minus 2, ID is 2,5, which I get from the curve there. I can see there ID is 2,5 and VGS is minus 2. From the graph, ID is then 3,4 when VGS is minus 1 and ID is 1,8 when VGS is minus 3. And then the peak-to-peak drain current therefore is 1,6. Okay, I can see there the peak there was 3,4, 1,8, 1,8 subtracted from 3,4 is going to give me a value of 1,6 milliamps. And the same is done for the D MOSFET, and the same is then done for the E MOSFET. So I can see here for the D MOSFET, the peak-to-peak drain current will be the highest, 2,8, then for the E MOSFET, and then lastly for the JFET. Right. Lastly then, circuit figure 914 uses a voltage divider bias to achieve VGS above threshold. The general DC analysis proceeds as follows using the E MOSFET characteristic equation, equation 8.4 to solve for ID. Alright, these equations are familiar from the previous chapter. VGS is equal to voltage divider R2 R1 plus R2 times VDD. ID is equal to the constant times VGS minus VGS threshold squared, and VDS is equal to VDD minus ID RD. So then finally the voltage gain expression is the same as for the JFET and the D MOSFET, but the AC input resistance is R1 in parallel with R2 parallel with R in the gate, where R in the gate is VGS over IGSS. Have a look at this last example. A common source amplifier using an E MOSFET is shown in figure 917. Find VGS, ID, VDS and the AC output voltage. Assume that for this particular device ID on is 200 milliamps at VGS 4 volts, VGS threshold is 2 volts and GM is 23 millisiemens, V in 25 millivolts. Let's have a look at the solution on the next page. So first I will go and calculate VGS 2,23, then for VGS at 4 volts. Remember the formula from the previous chapter, just take out K so I can work out the constant first. ID on, which was given, divided by VGS minus VGS threshold, also given squared, so it's 50 milliamps per square volt. So ID then is K times VGS minus VGS threshold squared, 2,65 milliamps. VDS 6,26 volts, then RD, remember there's a load resistor, I have to calculate RD in parallel with RL, 3 kilo ohms, so the AC output voltage gain V in, which is GM RD V in, 23 millisiemens, 3 kilo ohms, 25 millivolts, 1,73 volts. Alright, that concludes then section 9.1. You have to remember though, as I do with equations, you have to read through the section discussed, work through all the examples, do the relevant true false core circuit action core self tests, and in this case relevant basic problems are problems 1 to 23. Alright, concludes then section 9.1.